Now I'm recording. We spoke a little bit about oxygen depletion in the Baltic and the stability of maximum oxidation number in the presence of oxygen. But even number 4 here, like sulfites, they are quite unstable in the vicinity of oxygen. Simultaneous appearance of oxygen and sulfite ions, for example, is a difficult thing. This is actually used as a reducing agent and a preserve. Also, it's quite poisonous as a preservative to some foods, for example. Liquors and wine and such things are often added some sulfite. Not all wines, but several at least. In principle, to keep fungi and bacteria to a low level so they don't destroy the liquor. But these very reduced species, they have hardly any use except that they occur here and there in nature. For example, they bind to several transition metals very efficiently, which is a reason why they are should be termed as poisonous. Transition metal in their own environment, that may be, but transition metals in the active center of proteins, they shouldn't be bound to sulfides, because then they work differently. For example, not at all. So the redox potential and the acidity state is very important variables to describe how different compounds behave and in what form they occur. So how to describe this? Is it with a graphic representation, or we could of course also use analytical formulas, and we will use both. But I think it's good with a graphic representation because you get the overview. Analytical formulas are good when you need a certain value, and if you're not satisfied with, say, an approximate value in say, correctly within an order of magnitude or so. Everything is assumed to be in equilibrium. That is, of course, slight drawback, because very many processes in nature, they are not necessarily at equilibrium, but they could be in say, pseudo equilibrium, because there are high activation energies, so they could be metastable compounds. For example, humans, they are not in equilibrium with the atmosphere, luckily enough, because then we would all our carbon atoms should be carbon dioxide. Someone need to mute themselves. Or I can try to do that. So yeah, these equilibria. Here is a typical. Oh, I need my drawing plate. Here is a typical illustration with graphical concepts from a redox perspective. Sorry. Hey, sorry. Too early, you know, I miss. So here it's E. This is redox potential, some kind of electrical potential, high values to the right and low values to the left. And to the right here, we have a pH scale. This is much more well known, I think. High values to the right and low values to the left. So in that respect, both of them are similar. To make them even more similar, we can put a P in front of the E. The only thing that will change then is the values occurring on the number line here. But yeah, this is perhaps not very well known from before. You're used to redox potential, I think. But essentially, it's nothing strange with adding a P also. We will have a look at that. The similarity between these two, what do I mean? At high pH values, what do we have? We have few H+. And at low pH values, we have many H+ in the environment. So that is here. So, here we have a basic environment, and here we have an acid environment. Can you see this that I write?
We can.
Yeah, fine. And just using that observation and map it onto the redox case, here we have in the sorry, why does it jump? Oh, it was problems. Could be worse. So here we have few electrons or a low electron activity. An environment with the difficulties to find electrons in the environment. Low electron activity is the same as low hydrogen ion activity, which we call a basic solution. A solution with low electron activity, should we call that reducing or oxidizing? I think it's an oxidizing condition, because then something can oxidize, some material object can oxidize, producing electrons. And here in the low, at the low values of the reduction potential, we have many electrons available or high electron activity. Let's see how. So, and just so now they disappear. Yes. So, can we use these diagrams, for example? Here we can start at the right here in the acid-base version. So I depicted two different acid-base systems. Hydrogen fluoride, which is a not very strong acid, but quite strong acid with some pK value of, I don't know, something like 3.3 or something like that. And then the ammonia system with a pK value of, what could it be, 9.7 maybe? yes, they don't. They're not related in any other in any way, except that they are two examples of acid-base system. So in the case that we do take ammonium ion and mix with hydrogen fluoride, do we expect something to happen? Well, ammonium ion, they can exist at low pH values, also at high, but also at low. And HF molecules, they can exist at low pH values. So probably nothing happens. Ammonium ion and fluoride ions then. Well, they also have a certain area where they overlap. They have a common existence area. And I think then probably nothing happens, or not very much at least. One could of course claim that ammonium ion is weak acid and fluoride ions are weak bases. So they, in some part, they may react with each other, but that is only a few in very many particles. In order to do such determinations or detailed predictions, then you need to do analytical calculations. The majority of the ammonium ions and the majority of the fluoride ions, they will just stay and coexist with each other. However, in the last case here, hydrogen fluoride and ammonia, they don't exist at the hydrogen fluoride exists at acid environments and ammonia at basic environments. And an environment, or say a solution in a beaker, it can't be acidus simultaneously as it is basic. So these they can't coexist. Here the HF will deprotonate to form fluoride ions, while where does that hydrogen ion go? Well, it goes to ammonia, which will protonate and form ammonium ions. This is a way to actually use these kind of diagrams. Exactly the same could be said about redox diagrams, or similar things at least. Copper and zinc, if you put two plates on top of each other or in a solution, hardly anything happens because they can coexist. Copper 2+ and zinc metal, on the other hand, copper 2+ can exist only in electron poor or low electron activity surroundings, and zinc metal can only exist at high electron activity surroundings. So this will be a reduction of the copper ions to copper metal, and an oxidation, a reduction here and an oxidation here of the zinc metal. Copper ions and zinc ions, yes, they sorry, they have a common existence area, so there nothing happens.
I'm sorry.
Yeah.
I don't know if it's just me, but in the middle of the page, next to the arrows in the equations with copper and zinc, did you write things there?
Copper and zinc. No, I didn't wrote. Yeah, here copper ions.
Yeah, okay, because I can see that. I don't know about everybody else.
So there
I can't see either.
There is a blank area in the center. I see. Thank you. We'll see if I can figure out why. That is usually because we have only one Zoom window. Window. Now it's do you see it now?
Yes.
Yeah. So I'm not sure why, but when there are several Zoom windows open, they may hide each other, even though it's not visible on the screen. So, yeah, it's good that you tell me. Then if we continue. So when it comes to these sort of redox diagrams or redox discussions, we use either the reduction potential, or sometimes we should have a look at an alternative way also, including something called PE. This P does not necessarily means the minus 10 logarithm of the redox potential. It's the minus 10 logarithm of the electron activity, but we can just for the moment we can just look at the similarity between two different quite often used nomenclatures. Suppose you have a typical reduction of oxygen, for example, in an acid environment. Normally one would use Nernst formula or something like that for describing the redox potential variation with the, say, oxygen gas pressure or pH maybe. This is actually quite important. The hydrogen ions do actually affect the ability of oxygen to be reduced to the type of -2 oxygen that are present in water. If you look at the next picture, it's the same formula. Sorry, I need to turn that down. So it's the same formula, but here we give this is Nernst equation as you can find it in textbooks. It's the E value. This is a redox potential value, some constant E naught. In many textbooks, this naught is given with a horizontal line over it, but this is just a normal 0 digit, but I mean the standard reduction potential in this case. I don't have access to this easy, at least to this special symbol. So, but E equals E naught minus RT upon number of electrons. Here it's 4. So the number of electrons should be 4 times the logarithm of the reaction quote, the right-hand side divided by the left-hand side, and the concentrations if it's solutes, and otherwise if it's pure liquids, then sometimes some units occur, but formally one can always use the activity symbol. Are you familiar with activities?
Yes, somewhat.
Somewhat? And some other voice? Sure. Should we have a repetition of the concept of activity?
For me, it's really like connected to enzymes. That's what I think of.
Yeah. Okay, enzyme activity. It may be similar to this activity, but no, actually not. I need to find myself a glass of water. One moment. Now I'm back. Now let's see. We take a new share. So just make a quick test first. Can you see this line? Is it a single line over the whole screen?
Yeah, it's maybe it's a little bit weird on the right side right now.
Weird? I mean, is it
Yeah.
sawtooth or?
No, it's like duplicated. Yeah.
Duplicated like that?
A little bit more to the left. I think it's about it's where you got the menus or something like that. It looks like it gets worse when you go to the drop-down menus. That's what it looks like.
I see. So now then,
It's still like that, but not on the majority on the left side. So
is it somewhere here that it starts to become
no,
mortar? Say it in Swedish if you.
ja, någonstans, alltså det var precis till höger om det typ.
Här.
Ja, exakt där.
Ja, okay. Then I avoid that region.
Yeah.
I try to. So, hoppsan. I have problems. Now here we have a whiteboard, I think. Och så var det Kevin som pratade nyss.
Ja.
Ja, ser du linjen nu?
Ja, tyvärr.
Tyvärr. No, yeah, we try to use part of the whiteboard then. What do I mean by activity? Enzyme activity is one thing, but for example, you know, copper ion concentrations, this is measured in something like mole per cubic decimeter. This is a solution. I just used copper ions as an example of one ion. But if we also have a standard state of copper ions, then, well, this copper ion concentration, we don't know what it is. It's X mole per cubic decimeter. But the standard state is defined as a solution with 1 moles per cubic decimeter. And suppose we would use that and take the quotient of that, divide the unknown state with the standard state. Dividing the values is not a problem because X divided by 1 will be X. But what is this concentration divided by a standard concentrations? The units will disappear, and we will define something we call the activity of the ions. Remember, for example, what is the definition of pH? Sometimes in some books it says -10 logarithm of the hydrogen ion concentration. Is this correct? I ask you. Even don't trust the books. Everything that is written should be not taken as granted, but you should be suspicious. What is the units of pH? It's only numbers. No one has says any unit in pH any time. And then taking the logarithm of a concentration, why isn't the unit logarithmic concentrations? Yeah, it's simply because this is just a simplification. It's the -10 logarithm of the hydrogen ion activity. These wavy brackets are difficult. The activity do not, that is just a number. No units. And then taking the logarithm of a pure number produces then, of course, the a pure number. This is not so serious. Don't go out and distrust everything that you have learned so far. Because if you interpret this definition of the minus logarithm of a concentration, just take the value here. And forget about, be a bit sloppy, forget about the concentration. Because the value of the concentration in moles per cubic decimeter is the same as the activity of that very thing. And this is valid for any ion, not only the copper ions and hydrogen ions. What is the activity of pure water? How should we argue? Is it the same as the concentration of pure water, which equals 55, I think, moles per cubic decimeter? No, I think when this happens, we see unit 1, the figure 1 in equations. So then if we manipulate the concentration via some standard concentration, What is the standard concentration of water? That is pure water. Well, it's also 55. But it's quite cumbersome to write this concentration and then the standard concentration and make a quote of it every time you want to use this unit 1 in a equilibrium expression, for example. So then it's very convenient to have the activity concept. In some circumstances, you can actually see people using this concentration of pure water as 55 moles per cubic decimeter and put it in literally in expressions for equilibrium constants. That is not totally wrong, but it is at least something that you need to know about, because then the equilibrium constant would have a different value. And it wouldn't be connected to energies and such things, not easily at least. But defined with the activities it has, that makes the thermodynamic equilibrium constant.
So the activity value could be anything.
Yes.
It's not like a number between 0 and 1. It could be anything.
Yeah, I would say for solutions it could be it should be, say, bigger than 0, but to a large value. Is it negative? -1 moles per cubic decimeter? Is that a possibility? Very unlikely, but unless you have sorry, say that you have 1 moles per cubic decimeter of hydrogen ions, then you could claim that this is negative concentration of hydroxide ions, because hydroxide ions need to be added at least 1 moles per cubic decimeter in order to get a neutral non-acid solution. But this is the only case that we can have negative values. But for the moment, let's trust the books that claims that concentrations are never less than 0. It could have any value, yeah, but preferably bigger than 0.
Okay.
Yeah. So in the case of oxygen, I think it was something like this. And 2H2O. So if we should put up some, say, an equilibrium constant or a reaction quote, if we have equilibrium, then we call this reaction quote special value, equilibrium constant. Then it's the activity of water squared, because the stoichiometric coefficient here. And then it's the activity of O2 gas and the activity of H plus raised to the power of 4. And then it's a matter of taste whether you should include the electrons or not. Speaking about redox potentials, then we usually don't include the electrons, but treating this as a general equilibria, then we should perhaps add the electrons. But for the moment, we can skip it. So what will the values be? This is 1 because it's pure water, nearly. If it's dilute water, then say that it's only 99% water, then we will have 0.99 to the value to the power of 2. But then you need to have a good reason for what the rest of the solution is. Well, 1% solution could perhaps be the hydrogen ions or something like that. But for the moment, I suggest we put in a 1 because that is nearly close, at least in the case of 0.99, it's nearly close to. Hydrogen ions, we can use the value of the concentration and just raise it to the same power, but skipping the unit moles per cubic decimeter. What the activity of oxygen gas, for pure gases, it is said to be unity, but for dilute gases like air, for example, then if this is air, then it's something like 20%, and we can put in a value of 0.2 approximately. It's a difficulty connecting percent with activities, because if you have a percentage value of a gas in a gas mixture, you then you don't necessarily means volume by volume or molar percent, but what you should expect is the weight percent, and then you need to scale different molar weights with each other. But then we are getting into well, a lot of trouble. It's approximately 0.2 at least. So here we have an expression for the equilibrium constant, or if you want the reaction quote, if this is not at equilibrium. And very often we have oxygen that dissolves in water at a certain pH, and we have water and the solution is metastable, even though there may be an electron source close by. But when it is at equilibrium, then we need to argue that these electrons are also well set in some respect. For example, if there are organic matter in the water, you can aerate organic matter containing water, but and it's not at equilibrium directly, because at equilibrium that organic matter will probably be oxidized. Maybe details. Hoppsan.
I had a question.
Ja.
What did you say that the activity of a pure gas was? Was it 1? Did you say that?
Yes, yeah. Pure gases, pure liquids, pure solids, all of them has activity 1. There are sometimes stated that pure liquids and pure solids should be replaced by units in equilibrium conditions, and the reason for that is the definition of the activities, even though in many books it's just stated that replace them by units.
I see. Okay.
Yeah.
Thank you.
I really recommend the activity concept. It's quite simple, and it simplifies at least equilibrium calculations in many cases. Let's see, 9:43. What were we doing? So The equilibrium constant, or the rather the reaction quote defined in the same way, should be present in this bracket here. Taking the logarithm multiplied by gas constant and temperature and divided by this Faraday constant. These are just R and F are just numbers. They use them in SI units. It's 8.314 and 96,485. I think, yes. You may have to look it up in some internet page or textbook. Temperature could be anything, but it's usually, say, 25 degrees, 298 kelvins or so. It's just a dream, maybe, that we will have that temperature in the environment, but 293 is reasonable. If you instead use the other nomenclature with PE, it's nearly this similar expression, but you don't have the natural logarithm, you take the 10 logarithm, and this constant are T and F. The T is not a constant, it's a variable. It seems to be absent here. It's just the number of electrons. So temperature is actually part of this constant PE naught, while it's not present here in E naught. Yeah, maybe I don't want to go too deep into details about this. You see the similarity between these two expressions. And for example, if we know PE and PE naught, then we could calculate something about the reaction quote here. Assuming, for example, that the water activity is constant, that the oxygen come from the atmosphere, then we can calculate the pH or the acidity in this solution. I think we need a break. 9:45. 10 o'clock, is that okay?
It's fine for me.